All right, so we're going to do just one more thing about this proposition about elliptic curves over local fields, which is a result that came up in the one special talk that I gave about a relationship between pi and elliptic curves that I give sort of like for Pi Day when I'm teaching elliptic curves in the spring semesters. So this came up, and I wanted to mention this, that we can actually prove this now. That so remember that an elliptic curve has potential good reduction. An elliptic curve over a local field, there is potential good reduction if there is a finite extension, so a finite extension K prime, such that over that extension there is good reduction. So that over the residue field of the extension, now the elliptic curve is reduced. The reduction elliptic curve is smooth. So what I wanted to show is the following, that if you have an elliptic curve over a local field, then E has potential good reduction if and only if the J-invariant is integral. Okay, if you go case by case, this is what this is actually saying is that if there are no primes of multiplicative reduction, remember that the multiplicative reduction are the primes that are stable or semi-stable, but do not become good reduction. So what this is saying is that there is a prime of multiplicative reduction for your elliptic curve, if and only if that prime appears in the denominator of the J-invariant. Okay, so another way to read this is that E has multiplicative reduction if and only if the J-invariant is integral, or the J-invariant is not integral. At nu, so the valuation of the J-invariant is negative. Okay, so if you look for elliptic curves and you look at the J-invariant, by looking at the primes that divide the J-invariant, the denominator of the J-invariant, those primes are necessarily bad multiplicative, and then you're not going to have potential good reduction. But if the J-invariant is integral, if it's over Q, if the J-invariant is an integer, or if you're working over a p-adic field, if that J-invariant is integral at that prime P, then you're going to have potential good reduction at that prime. Okay, so let me prove this. Recall that in the previous lecture, what we did to prove the semi-stability theorem was that to prove that there is always an extension of good reduction was to switch to Legendre normal form. And since potential good reduction doesn't change under finite extensions, if you go up to a finite extension, still there will be potential good reduction if there's an extension above that one. And J-invariant, the J-invariant is invariant under base change. So we can extend our field if necessary so that we have a Legendre normal form. And the Legendre normal form you get through a finite extension. We explained that last time. So we may assume that E is given by a Legendre normal form. Oh, don't misspell Legendre. Legendre normal form, or do a change of base if necessary, or do a finite extension otherwise. So E is given in the form x minus 1, x minus lambda, okay, with lambda non-zero or 1. Great. We're assuming the characteristic is not 2. The characteristic of little k is not 2, just in case. Okay. Now, let's start with, assume first that the J-invariant is integral, and we are going to prove, so we're going to prove this direction. That arrow doesn't look good. So I'm going to prove this direction. So I'm going to assume that the J-invariant is integral. Then if I rewrite my equation for the J-invariant, so the J-invariant, I have a formula for the J-invariant here. I do. So it turns out that the J-invariant of E in terms of lambda is going to be, it's 1 minus lambda cubed divided by lambda squared 1 minus lambda squared. Okay, so that equation, what it tells me is that if I write this as a polynomial in lambda, I get this equation. And the coefficients here are in R because J is in R. So the coefficients are in R. And if you chase what is the highest degree here, is going to be, what is it? It's going to be, there is lambda to the 6, I believe, in here, and it's going to be monic. Okay, so it's monic in lambda. So lambda satisfies a monic polynomial with coefficients in R. Therefore, lambda itself is integral. Okay, and lambda cannot be 0 or 1 modulo m, because if it was, what would happen? If, for example, if lambda is 0 modulo m, then what I get is that this is 0 modulo m, and then this piece would be 0 modulo m, and what I get is that this would imply that 1 is congruent to 0 modulo m, which is a contradiction. Okay, and if lambda is 1, what happens? This is again 0, and this is again 0, and again 1 is congruent to 0 modulo m. So it cannot be congruent to 0 or 1 modulo m, and therefore what happens is that the delta is non-zero. The delta for a Weierstrass, for a Legendre normal form, remember we gave it last time, it's this form. So this is non-zero modulo m, and the equation is given over the integers, and therefore we have good reduction. Okay, therefore the model has a good reduction. So that's what we wanted. Not just even potential good reduction. We found a model where there is actual good reduction. It's starting from the fact that the J-invariant was integral. Okay, so now I'm going to go the other direction. So this is half of it. So now in the other direction, we are going to go this way. So we're going to assume that there is potential good reduction. Okay. So let K prime over K be that finite extension, a finite extension such that E over K prime has good reduction. Therefore, in that extension, we have that the new discriminant is a unit in R prime and C4 prime, or C4 that is an integer, and therefore the J-invariant actually has a formula C4 prime cubed divided by delta prime. Since delta prime is a unit and C4 prime is an integer, this is integral. Okay, I'm only dividing by a unit, so this is an integer of R prime. But the J-invariant doesn't change upon extensions, so the J-invariant was in K, and therefore I get that the J-invariant is both in K and in the ring of integers of R prime, but by definition, well, not by definition, but the elements that are integral in R prime and in K, those are the ring of integers. So that's not hard to prove just using evaluations. Okay, so so the J-invariant is integral as we wanted to prove. Okay. And the reason why this came up in the class, in the lecture about pi, we were trying to prove that e to the pi times the square root of 163 is really close to an integer, and we needed that the J-invariant was an actual integer. So here's a fact that I'm not going to prove here because we would need to develop the theory of complex multiplication farther, that we have that if you have an extension, a finite extension of QP, and if E over K has complex multiplication, then it turns out that E over K has potential good reduction. Okay, so always the elliptic curves with CM have potential good reduction, and therefore the J-invariant, by what we just proved, is an integer. And therefore, if E over Q is an elliptic curve with CM, then the J-invariant must be an integer. So it's an integer, so it's in ZP for all P, and therefore the J-invariant of an elliptic curve over Q with complex multiplication must be an integer. Okay. So for example, I hope that I get these right because I always mix them up. But the elliptic curve, so this elliptic curve over Q has CM, has extra endomorphisms, which we saw. The extra endomorphism is given by xy is sent to minus x comma iy. Okay, but in any case, it has CM by z adjoin I. Okay, and the J-invariant then has to be an integer, and the J-invariant in this case is 1728. On the other hand, we also saw that the elliptic curve, that this elliptic curve has CM. You can change x by x times a cube root of unity, and then you would get, so xy goes to rho x comma y. It's the same. It's also a point on the curve, so that's an endomorphism. This has CM by the ring of integers of Q adjoint the square root of -3, and the J invariant is indeed an integer. It's just 0. Okay, and there are more exotic examples of elliptic curves with complex multiplication over Q, and they all have integral J-invariants. And if you go up to number fields, if I give you some like, some algebraic number of some sort, you can tell, one way to tell is there a CM is if that J-invariant is integral. Is it an actual algebraic integer or not? If it is not an algebraic integer, there is no CM. If it is an algebraic integer, that doesn't mean that it has CM. So every elliptic curve with a J-invariant that is an integer does not have automatically CM. In fact, there's only 13 J-invariants that are CM. So every integer, not one of those 13 numbers, it's not a J-invariant with CM. But it is a condition, it is a necessary condition that the J-invariant has to be an integer, which is what we use in that class about pi. So I'm going to stop here, and then I'll resume in another video.